We are going to start module 6 of chapter 5, where we will be talking about one of the most important theorems in linear algebra called the spectral theorem, which is also called the spectral decomposition theorem because this theorem will give us a very special decomposition for operators which are either normal or self-adjoint. We have already seen that for a normal operator, if the base field is the field of complex numbers, then it can be diagonalized, and the same thing is true for a self-adjoint operator. But what we will see in this spectral theorem is that not just that it is similar to a diagonal operator, but it can be written as a sum of the form lambda 1 T1 plus lambda 2 T2 and so on lambda k Tk, where these Ti's are orthogonal projection operators and lambda i's are eigenvalues. Let us see the spectral theorem. The spectral theorem. Let V be a finite dimensional inner product space over the field F. F is the field of real or complex numbers, and T a linear operator on V with distinct eigenvalues lambda 1, lambda 2 and so on up to lambda k. Assume that T is normal if F is the field of complex numbers and that T is self-adjoint if F is the field of real numbers. Let Ni denote kernel of T minus lambda I, that is the eigenspace of the operator T with respect to the eigenvalue lambda I for I is equal to 1, 2 and so on up to k. Let Ti denote the orthogonal projection of V on Ni. Then the first part of the theorem says that V is a direct sum of n1, n2 and so on up to nk. Second part says if Wi is given by this direct sum of nj's for j other than I, then Ni perp is equal to Wi. The third part, for every ij within 1 and k, Ti Tj, the composition, is equal to Ti if I is equal to j, and it's the zero operator if I is not equal to j. The fourth part says that I is equal to T1 plus T2 and so on up to Tk. This is what is called the decomposition of the identity operator. And the fifth part says that T is equal to lambda 1 T1 plus lambda 2 T2 and so on up to lambda k Tk. So this is the so-called spectral decomposition of the operator T. Proof of part 1. T is normal or self-adjoint, and therefore we know that T is diagonalizable, assuming of course F is either C or R, and therefore we have this direct sum decomposition of the vector space V given by n1 direct sum n2 and so on nk, where n1, n2 and so on nk are the eigenspaces. Part 2. Let V belong to Ni and W belong to Nj for j not equal to I. Then inner product VW is 0 and Wi is contained in Ni parp. we have by 1 dimension of Wi is equal to summation of dimension of Wj for j not equal to I, which is the same as dimension of V minus dimension of Wi. And we know that dimension of Ni perp is dimension of V minus dimension of Ni. Hence, Ni perp is equal to Wi. Part 3, each Ti is an orthogonal projection, hence Ti square is Ti. Now, if I is not equal to j, then we obtain Ni intersection Nj is the singleton 0 vector, because Ni is range of Ti and Nj is range of Tj. Therefore, Ti Tj is the 0 operator. Part 4, the operator Ti is an orthogonal projection of V on Ni, and therefore range of Ti is Ni, and a kernel of Ti is range of Ti perp, which is Ni perp, and that is equal to Wi. Therefore, given V in the vector space V, we have V is equal to V1 plus V2 and so on up to Vk, where Vi belongs to Ni and Ti V is Vi. Hence, I is equal to T1 plus T2 and so on up to Tk. And finally, given vector V in the vector space V, we write V as V1 plus V2 and so on up to Vk, where Vi belongs to the eigenspace Ni, then T of V, which is T of summation Vi I equal to 1 to k, which is summation T Vi I equal to 1 to k, that is equal to summation lambda I Vi I equal to 1 to k, because Vi's are in the eigenspaces, therefore they are eigenvectors with respect to the eigenvalue lambda I, and that is equal to summation I equal to 1 to k lambda I Ti V, because Ti's are the orthogonal projections, and that is the same as summation I equal to 1 to k lambda I Ti of V. Therefore, T is equal to summation I equal to 1 to k lambda I Ti. Now, a definition, it says that the set of these distinct eigenvalues lambda 1, lambda 2 and so on lambda k for the operator T on a finite dimensional inner product space V over F is called the spectrum of the operator, and this decomposition T is equal to lambda 1 T1 plus lambda 2 T2 plus so on lambda k Tk, where lambda 1, lambda 2 and so on lambda k are the distinct eigenvalues and T1, T2 and so on Tk are the orthogonal projections, is what is called the spectral decomposition of the operator T. And in matrix form, if Bi is an orthonormal basis for the eigenspace Ni, then the union of these Bi's, what is denoted by B, is an orthonormal basis for V, and the matrix representation for the operator T is given in this block form, where you can see that lambda 1 ID1, lambda 2 ID2 and so on lambda k IDK, where ID1, ID2 and so on IDK, they stand for the identity matrices of sizes D1, D2 and so on Dk. Lambda 1 so on up to lambda k are of course the distinct eigenvalues, and all other entries are 0. We now see some interesting corollaries of the spectral theorem, and after that we will do some computation with specific examples to exhibit these orthogonal projection operators. We will see that often computing these orthogonal projections, or before that computing an orthonormal basis, it may not be that easy. So we will understand the spectral theorem better with some simple examples. We now prove a few important corollaries of the spectral theorem. The first one says, if V is a finite dimensional inner product space over the field of complex number C, then the operator T is normal if and only if T star is equal to f of t for some polynomial f over C. Suppose that T is normal with the spectral decomposition T is equal to lambda 1 T1 plus dot 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 plus lambda k Tk, then T star is equal to lambda 1 bar T1 star plus so on plus lambda k bar Tk star, and that is equal to lambda 1 bar T1 plus so on up to lambda k bar Tk. Why? Because Ti's are orthogonal projections, and therefore we have that Ti star is equal to Ti for all I. Now we can use the very important Lagrange interpolation formula to choose a polynomial f such that f of lambda I is equal to lambda I bar for I equal to 1 to k. Then f of t, which is summation I equal to 1 to k, f of lambda I Ti, and that is the same as lambda I bar Ti, I equal to 1 to k, and that is equal to T star. Conversely, if we are given that T star is equal to f of t for some polynomial f over C, then T commutes with T star, since T commutes with every polynomial in T, and therefore T is normal. Another corollary, let V be a finite dimensional inner product space over the field of complex numbers. Let T be a normal operator on V, then T is self-adjoint if and only if every eigenvalue of T is real. Proof: let us write the spectral decomposition of the normal operator T given by T is equal to lambda 1 T1 plus so on up to lambda k Tk. Let us assume that every eigenvalue of T is real. Then T star, which is the same as lambda 1 bar T1 star plus so on up to lambda k bar Tk star, and that is the same as lambda 1 T1 and so on up to lambda k Tk, because each lambda I is real, and that is equal to T. Therefore, we have proved that T is self-adjoint, and conversely, if T is self-adjoint, then we already know that every eigenvalue of T is real. Another corollary, let T be as in the spectral theorem with a spectral decomposition T is equal to summation lambda I Ti, I equal to 1 to k, then each Ti is a polynomial in T. So, T is normal if the base field is C and self-adjoint if the base field is R. Lambda 1 etc. up to lambda k are the distinct eigenvalues, and then this corollary says that the orthogonal projection operators T1, T2 and so on Tk are somewhat special. In fact, they are polynomials in T. Proof: let us choose polynomial fj for every j in between 1 and k such that fj of lambda I is 0 if I is not equal to j, and fj of lambda j is equal to 1. Then if we take fj of t, is the polynomial expression in T given by the polynomial fj, then it is nothing but fj of lambda 1 T1 plus so on fj of lambda k Tk, and that is the same as Tj because fj of lambda I is 0 whenever I is not equal to j, and only fj of lambda j in 1, therefore only Tj survives. Corollary: let V be a finite dimensional inner product space over the field of complex numbers. The operator T on V is unitary if and only if T is normal and mod lambda is 1 for every eigenvalue lambda of T. If T is unitary, then it is normal, and every eigenvalue of T has absolute value 1. Let T be is equal to lambda 1 T1 and so on up to lambda k Tk, the spectral decomposition of the normal operator T. If mod lambda is equal to 1 for every eigenvalue lambda of T, then Tt star is equal to lambda 1 T1 plus so on up to lambda k Tk times lambda 1 bar T1 star plus so on up to lambda k bar Tk star. Now T1 star is T1 and so on, Tk star is Tk. So we get this expression lambda 1 T1 plus so on up to lambda k Tk multiplied by lambda 1 bar T1 plus so on up to lambda k bar Tk, and this gives rise to mod lambda 1 square T1 plus so on mod lambda k square Tk, and that is the same as T1 plus so on up to Tk because mod lambda I is 1 for every I, and therefore it is equal to I, that is by the spectral theorem. Hence T is unitary. Let us now see some examples, and this will help us understand the spectral theorem better. Let A denote this symmetric matrix given by 1 0 1 in the first row, 0 1 0 in the second row and 1 0 1 in the third row. It is a real symmetric matrix and hence diagonalizable. It has 3 distinct eigenvalues 0, 1 and 2, and each eigenvalue has algebraic and geometric multiplicity 1. We have seen before that this set of vectors 1 over root 2 1 0 minus 1, then the vector 0 1 0 and 1 over root 2 1 0 1 is an orthonormal basis for R3 consisting of eigenvectors of A. Therefore, A is equal to Q D Q inverse such that D is this diagonal matrix where the principal diagonal entries are nothing but the eigenvalues 0 1 and 2, and Q is given by this 3 cross 3 matrix where the first row is 1 over root 2, 0, 1 over root 2, 0, 1, 0, then minus 1 by root 2, 0, 1 by root 2. Let us now write down the orthogonal projection operators for this example. There are 3, 1 each for each eigenvalue, and these are with respect to the orthonormal basis given by T0, T1 and T2, where T0 is the 0 matrix, T1 is this 3 cross 3 matrix where there is only one non-zero entry, namely 1 in the 2, 2 position, and T2, which is this 3 cross 3 matrix with first row 0, second row 0, 1, 0 and the third row 0, 0, 1. Therefore, the spectral decomposition in this case is A is equal to 0 times T0 plus 1 times T1 plus 2 times T2. Another example, A is this real symmetric matrix, and we know that it is diagonalizable. Then the eigenvalues are 2 and 8 with algebraic and geometric multiplicity 2 and 1 respectively. We have seen before that this set 1 by root 2 minus 1, 1, 0, 1 by root 6, 1, 1 minus 2 and 1 by root 3, 1, 1, 1 is an orthonormal basis consisting of eigenvectors of A. And therefore, the matrix A is equal to Q D Q inverse, with D being the diagonal matrix, where the principal diagonal entries are 2, 2, 8, which are the eigenvalues, and the matrix Q is given by minus 1 by square root of 2, 1 by square root of 6, 1 by square root of 3 in the first row, 1 by square root of 2, 1 by square root of 6, 1 by square root of 3 in the second row, and 0 minus 2 by root 6, 1 by root 3 in the third row. Let us see the orthogonal projection operators for this example. There are 2, 1 each for each eigenvalue, and these are with respect to the orthonormal basis given there, T2 and T8. So, T2 is the one corresponding to the eigenvalue 2, and that is the 3 cross 3 matrix whose first row is 1, 0, 0, second row 0, 1, 0, third row 0, 0, 0, and T8, which is this 3 cross 3 matrix where the first 2 rows are the 0 rows and the third row is 0, 0, 1. Therefore, the spectral decomposition that we get is 2 times T2 plus 8 times T8. We have learned spectral theorem, spectral decomposition for normal and self-adjoint operators. We have also seen some very important corollaries, and we have seen that the orthogonal projections which actually give us the spectral decomposition, they can be expressed as polynomials in the operator T. We have also seen some spatial situations for unitary operators, and now we will see them more closely. We will understand the unitary operators and see their full characterization, and also learn some geometry of orthogonal and unitary operators.